It was August 7th, 1997. The vehicle was all ready to go out on the pad. It's a busy morning, launch morning, so we were all had a little bite to eat, got into the suit room, got all suited up. It takes quite a while to do that if you've seen a previous flight. But everyone was in great spirits. Everyone was excited to go. Got beam away from the breakfast table. And Steve's all excited. And last but not least, Bjarne got his suit all checked out, and he was ready to go also. The vehicle was out in the pad. It was fully loaded with propellant and fuel, and it was a flawless countdown. It was all ready to go. We departed the operational checkout building, the crew quarters where we stay, for our trip, hopefully our only trip out to the pad for this flight. And due to the great weather and the countdown, it happened our first try. Once in the white room, we get a little bit more equipment on, our harnesses for our parachutes and oxygen bottles. And now we're going to show you inside the cockpit, climbing, kind of doing a chin-up here to get into the seats. A little bit different view than you normally see. Joe Tanner was our astronaut support person to strap us in, try to get comfortable. And on the middeck, while that was happening, Steve was getting in the MS3 seat. Kent's getting his helmet on. Jan's doing what she always does. Now, actually, Jan, if you see on the left down there, is in the cockpit already. And the last but not least was Beamer, or Bob Kerbeam, to get in the MS2 seat, our flight engineer for Ascent. The middeck's ready to go with Steve and Bjarne all strapped in. With everyone aboard, it's time to remove the white room. It rotated back, as you can see. At 2 minutes, they give us a call to close our visors. So we put our visors down and turn our suit on, O2 on in preparation for start. 6.5 seconds, there goes the main engines, which is always really a beautiful feeling inside the vehicle. You can see the tank kind of does a little twang. And at T0, we're on our way. And now we're going to show you what that looked like from inside the cockpit, the same exact sequence. There's an engine start, a lot of rumbling, a lot of vibration. You'll see the big jolt here for liftoff. Boom, there goes liftoff, and we're on our way. And if you watch the lighting condition, as we cleared the tower, we did a big roll maneuver to align ourselves for our ascent, and you can see the lighting conditions change, and the sun winds up right in Jan's face for pretty much the whole ascent. Well, as you know, it doesn't take long to get out of Dodge here when those engines get going and start pushing and all that thrust gets going. So we were feeling acceleration about this time. We're a high inclination flight going up the eastern seaboard, 57-degree inclination, going up to about 160 nautical miles. The launch was in kind of a hazy conditions, but we could see SRB set. So 2 minutes after launch, we got rid of the SRBs. And now we're going to show you what that looks like inside the cockpit, the big flash, so you'll have an idea of what we see at SRB set. So it definitely gets your attention. You know the boosters are now separated. We can put our visors up at that time and ride the 3 shuttle main engines to the orbital speed and orbital altitude for the rest of the ascent. After we get off the tank re-enters the atmosphere. That gives you some idea of our speed. This is real time. This is not sped up. Some idea of our speed at the low altitude we're at. And once we're on orbit, it's now time to turn the rocket into an orbital space station. So we open the big payload bay doors and get ready for payload ops.
Once we have the payload bay door open, we can start our payload operations. This is a very busy flight with over 40 different payloads, some of which you see here in the payload bay. In the middle of the payload bay is the Krista SPAS, one of our primary payloads, which was a scientific satellite looking at chemicals in the ozone layer. And on the very first day, we had to deploy Krista SPAS to give it as much time as we could on orbit. And here Steve and I are in the aft flight deck getting ready for those robotic operations with the shuttle remote manipulator system, the Canadian Robot Arm on the shuttle. And here I am maneuvering the Canadian RMS to the Krista SPAS grapple fixture so that we can grapple the Krista SPAS, as you see here, and lift it up out of the payload bay and take it over the payload bay and get it ready for deploy. And here it is just before we release it. We're activating all of the experiments and instrumentation on the Krista SPAS satellite, which was controlled by the Germans from Kennedy Space Center, Payload Operations Center. Here's a release of the RMS from the grapple fixture that's on the Krista SPAS and we send it on its way to a 9-day scientific mission, and we retrieve the crystal spas on the 10th day of the mission. To separate away from the crystal spas, we Rommel maneuvered the orbiter with some separation burns to get us away from the crystal spas, and you can see the crystal spas as it is separated from the orbiter by moving the orbiter away from it. They were able to get a lot of data in those 9 days. As you can see here, it is now fully separated from the orbiter.
Although Crystal was our main payload, our payload bay was very full. As you can see here, forward in the orbiter is to your left, and the first payload you see there is the Japanese Robotic Arm, or the MFD, the Manipulator Flight Demonstration. Then the next bridge you see there is the Technology and Applications and Science Experiment, which had a bunch of engineering models to be tested in zero-G and also scientific experiments. And in the aft, and we'll get a close-up of that soon, you'll see another hitchhiker bridge, and that was the International Extreme UV Hitchhiker. And it had a multitude of payloads looking in the ultraviolet at stars, the Earth's atmosphere, any interaction of the shuttle with the upper atmosphere. A lot of these facilities had optical systems, and so we had a lot of hitchhiker doors, as these are called, which closed to protect them from debris during some of the more sensitive times of flight. We also had some Middeck experiments, and this is me taking a media sample out of the bioreactor demonstration system. What I was doing, I was growing colon cancer cells to much larger aggregates than we could do in 1G environment, both for colon cancer research and cell research. And there you see the aggregates, and they grew to about 3 or 4 times larger than you would see in 1G.
Just continuing on with some of the Middeck experiments, this is Kent Rominger, or Rommel as we call him, getting ready to do the solid surface combustion experiment. And this is an experiment that is flown on a number of shuttle missions and builds up the knowledge of how materials burn in the zero-G environment of space. In this case, we're burning a plexiglass, a type of plexiglass, and there you see the ignition of that plexiglass. And we filmed the burn for about 10 minutes before the flame, this little blue flame finally extinguished. This is the Swiss telescope used to have a look at the Hale-Bopp comet through the side hatch window. And it views the comet in the ultraviolet, which gives us a better signature of some of the ions and elements coming off the comet that give off light in the UV. Steve spent a fair bit of his time during the mission doing this experiment. And that little bright spot there just to the left of center is the actual comet. You can't see it very well because it's a long distance from the Earth, but by summing up a lot of these images, the scientists can pull out some of the structure in the comet itself. There's Jan and myself just preparing the microgravity vibration isolation mount for one of the experiments we're doing on it. This system isolates experiments, fluid dynamics and material science experiments from the vibrations of the shuttle. And we'll see in the next shot that not only can we isolate, but we can actually shake an experiment with very well-controlled acceleration profiles to look at the sensitivity of experiments, typically the kind that we're going to be doing at a space station, to the vibrations. And here's a little student experiment we used MIM to do where we can visualize the motion of rather large-looking molecules that would behave the same as molecules in the air around us here today.
Another robot arm on the space shuttle on this flight is the Japanese Manipulator Flight Demonstration. It's a small robotic arm, about 5 feet long. As you see here in the payload bay, Steve and I were the operators of this. We're taking it from the stowed position to the operational position where we can maneuver it around. This is the real-time speed of it. It's a very precise instrument, so it's therefore very slow, but it's very functional. We can use it on the space station to take experiments off of a pallet, put them inside of a scientific airlock, or to do very fine tasks that we'll need to do on the space station. One of the things that we did on our flight to demonstrate this capability was we took this arm, which has a grapple fixture at the end of it, attached it to the box you see there. We called it orbital replacement unit. We attach it to the box and unscrew some of the bolts that are attaching that box to its plate. And we actually moving this around to test the performance of the arm and test its capability with a a load on the end of the arm. So we moved this orbital replacement unit around, and that's a similar type of activity we'll be doing with this arm, which is on the end of a very long arm on the space station. So we just tested the small, fine arm portion of what will fly on the space station. Another thing we did with this arm was we attached the arm to this door and actually unlocked the door, and we used the arm to open up the door. We did this with a program mode. We also did a lot of operations with some control from the ground, not just with the crew on the flight deck operating the arm. So this demonstrated a lot of capability for the future, and it performed very well. This is sped up a little bit, this function in the last scene you saw. We celebrated the success of this arm by eating some Japanese curry rice. You notice the chopsticks and rice and curry, which was just delicious. We also had a little free time later in the flight when we got an extra day, and one of the things our folks did was some fluid experiments. Fluids tend to form a ball because of the surface tension. They form a sphere, and here we're trying to join the red sphere and the water together, and we were successful after a few tries. Another typical middeck activity is exercise. When you're in space, your cardiovascular system doesn't have to work as hard, so we have to exercise to make sure it works fine.
We stayed busy on the flight deck as well throughout the flight. Along with a lot of the payloads came pointing constraints, pointing at various planets, stars, the sun, and back at the Earth. So Kurt and I both stayed busy putting in digital autopilot inputs to point at the different payloads at that. Also on the flight deck, you're usually busy with Earth ops, and just to give you an idea, we bring back more than 3,000 photos of the Earth. And here's some of the Earth going by at over 17,000 miles an hour. And the Earth observation scientists, as well as oceanographers, meteorologists, particularly interested in this view. This is Super Typhoon Winnie, and we were fortunate enough to pass right over the eye of it. It's a very distinct eye. You could see the blue water through the eye. And also, Super Typhoon is hundreds of miles across. This is probably 300 to 400 miles across that you're looking at. And the way we get these photos, that was video that you saw, but the stills that we're going to show you later are from several different sources. We use a Hasselblad camera. It's a 70mm format, and that does the majority of our Earth ops work. And we had just seen Beamer with one of those cameras. We also, though, carried a Linhof camera, which just brings back gorgeous photos, and that's because the negative on that is a 4-inch by 5-inch shot. And a lot of times, we're busy doing other payloads, such as this. Somebody floats up to the window and says, hey, look at this target going by. What is this? And so we kind of scramble for the cameras. In this case, it happened to be the Aurora. The video here is black and white. It doesn't really do it justice, and we've got slides later on to show you, but it was a gorgeous green color. It's down the south of Australia, the Southern Lights. I'd like to transition now into the rendezvous day. Here we are on rendezvous morning, getting ready on flight day 10 to go pick up Krista Spas, and it really is a team effort. It takes everybody in the crew was involved, from Kurt doing the manual flying, me doing some flying up front, Steve running a handheld laser. Here we are approaching on Krista Spas, and hours before we get this close to it, we're doing a set of burns to go ahead and phase ourselves in and close in on Krista. From the time we're within about 1,000 feet, it's manual flying, and Kurt at the aft station has it positioned here at the arm. If we were only going to grapple Krista, we would have done it at that point. But along in our flight, we had a detailed test objective, which was to go ahead and simulate a docking on a future space station mission coming up, where Kurt flew Krista right into the payload bay at a very precise rate. And once it was just broke the mold line of the payload bay, backed back out. And to me, it's always amazing that here you've got a 7,000-pound satellite, and we have probably a 250,000-pound at this point orbiter, and we can control that orbiter to a 0.1 foot per second plus or minus 0.03 and very precisely fly it into the grapple.
Well, as you can see, Kurt did a great job flying the orbiter right up around Krista, and he offered just to berth it for us without using the arm at all. And we politely declined that offer, and so Jan took control of the arm. And this is Jan flying in to grapple the Krista Spas satellite. And it's a very gentle maneuver, and here it is ready to get put back into the payload bay. Your eyeballs are essential tools up there in orbit, especially when you're doing robotics operations like we did a lot of in flight. Here's Jan looking out the overhead window, and this is kind of an unusual view where we've got a camera up on the arm looking back down at our crew compartment, this teeny little spot up there in the heavens. And I don't know if you can see Jan looking out the window there, but it's a really important part of doing accurate robotics operations. In the future, however, we're going to have to learn to rely on other sensors other than eyes. We won't always be able to see out of the space station to see our arms. You see targets on the arm here and also targets on our payload, Krista Spas here. These are for a Canadian-developed synthetic vision system that gives you a computer representation of where the payload is in relative to the payload bay. We brought the Krista Spas right down over the crew cabin on the arm in order to test this system that used these spots as tracking targets. And you can see them here on the telescope of the Krista Spas just about 5 feet over our head. Very dramatic view. We let the sun go down and we kept lights on it, and you can see it even in the dark. We're able to track the targets. And speaking of the sun going down, as a first-time flyer, I found that to be one of the really spectacular sights in orbit. And it comes out even well on video.
Well, unfortunately, after 11 days, 20 hours, and 27 minutes, it's time to put the orbiter back on the ground, bring it back home, both the crew and the vehicle back home to the Kennedy Space Center. We started our entry well on the other side of the Earth around south of India, Australia time frame or position. We slowed the orbiter down from its just over 17,000 miles an hour. As you see here, we had an early morning landing, and the glow of the early morning sun through the atmosphere was quite impressive. Approaching overhead, we started a big right-hand turn about 280 degrees to align the orbiter up on final for landing at Kennedy Space Center runway 33. We actually did a new kind of technique on the landing. We used short field speed brake, which is a technique to help control our energy in case we have tailwinds. And we were the first landing ever to use that, and it worked exactly as planned. The orbiter was my first chance to fly the orbiter. It flew very nicely, just like some of the training that we get here at Kennedy or at JSC and at White Sands and Kennedy Space Center. Rolling out on final, approaching the 300-foot point, Kent put the gear down. We crossed the threshold around 230 knots, looking for a touchdown around 195 knots. Right now, Kent's telling me all the right things to do, trying to make sure I get it right the first time. And we touched down about 3,000 foot down the runway. Drag chute came out right away. And just a little bit of different view here as we look down the runway. Again, the drag chute's out, and the speed brakes and the vertical tail start opening up to slow us down. As the drag chute comes out, it disreese, opens up fully to cushion the nose touchdown. And now we roll safely down the runway at Kennedy Space Center after going something over 4.7 million miles.